Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear student, Assalamu alaikum. Today I will discuss about the sulfur-containing unsaturated heterocycles and will specifically talk about the five-membered unsaturated sulfur heterocycle thiophene. Contents of today's lecture include sulfur-containing unsaturated heterocycles, in which I will discuss about the 3-membered, 4-membered, 5-membered, as well as 6-membered sulfur-containing unsaturated heterocycles. Then I will discuss about the structure and physical properties of 3-membered, 4-membered, and 5-membered unsaturated sulfur-containing heterocycle. And then we'll discuss about the natural occurrence of thiophene, and we'll discuss about the various methods for the preparation of thiophene molecule. Sulfur-containing unsaturated heterocycle. The simplest sulfur-containing unsaturated heterocycle is mentioned over here. As one can see, this is a 3-membered sulfur-containing unsaturated heterocycle. Its common name is thiacyclopropene. Thia word is used for the sulfur, while this is a cyclopropene molecule. And the IUPAC name is thyrene. The second one, sulfur-containing unsaturated heterocycle, is the 4-membered compound, and its common name is thiacyclo-2-butene. As one can see that this is position 1, this is position 2, and at 2 position there is unsaturation. So for unsaturation, the E and suffix is used. So the second sulfur-containing unsaturated heterocycle is a thiacyclobutene molecule, and its IUPAC name is 2-hydrogen thiate. The third one, sulfur-containing unsaturated heterocycle, is the most important one, and that is the 5-membered ring, and its common name is thiophene, while its IUPAC name is thiol. And today I will discuss specifically in detail about the thiophene or thiol molecule. And the last one is the 6-membered unsaturated sulfur-containing heterocycle, and its common name is 4-hydrogen thiopyran. 4-hydrogen because at 4th position it is saturated, so its common name is 4-hydrogen thiopyran, while IUPAC name is thiene. So I will discuss about these sulfur-containing unsaturated heterocycle one by one, starting from thyrene molecule. So thyrene is a very unstable species because it has a poor pi electronic system, and it is anti-aromatic in nature because 4 pi electron in cyclic conjugation and have not been absorbed. It means that it is not prepared because it is highly unstable. This is the structure of thyrene molecule. It consists of 2 carbon atom, 2 hydrogen atom, and 1 sulfur atom. And as it is highly unstable and it is an anti-aromatic compound, it consists of 2 pi electron in 4 pi electrons. So 2 non-pair electron is present on the sulfur, and it is in conjugation with this 2 pi electrons. So overall it consists of 4 pi electron, and it's an anti-aromatic compound, and we know that anti-aromatic compounds are highly unstable. So it's so unstable that it cannot be synthesized in the laboratory. However, only one example, the substituted thyrene molecule, has been found to be isolated, which is formed by the photolysis of 4,5-bis trifluoromethyl 1,3-dithiol to thione at low temperature. So only this trifluoromethyl substituted thyrene molecule is reported, while the unsubstituted thyrene molecule is highly unstable and anti-aromatic. Therefore, it is not reported. So we don't know about the physical properties or chemical properties of these molecule. Next is the thiate molecule, the 4-membered unsaturated sulfur-containing heterocycle. Thiate is a heterocyclic compound containing an unsaturated 4-membered ring, as one can see over here. Here is an unsaturation. It consists of 3 carbon atoms. and 4 hydrogen atom, 1 hydrogen here, 1 hydrogen here, and 2 hydrogen at this saturated carbon, and consist of 1 sulfur atom. And thioates are generally not very stable, and only its derivatives are reported. So similar to thyrene molecule, thioate is also highly unstable, and its synthesis is not reported yet, so its physical and chemical properties are not reported. The next is thiophene molecule, and I will discuss about the structure, physical properties, as well as synthetic methods of thiophene in detail in today's lecture. So starting from the structure of thiophene, thiophene is a heterocyclic compound, consists of 4 carbon atom, 4 hydrogen atom, and 1 sulfur atom. The structure is mentioned over here. One can see that it consists of 1 sulfur atom and 4 carbon atom, and each carbon atom carrying 1 hydrogen atom. So its chemical formula consists of 4 carbon atom, 4 hydrogen atom, and 1 sulfur atom. The molecule is planar, and it is aromatic in nature and highly stable as compared to the thyrene and thioate molecule, because it consists of 6 pi electron, 2 pi electron here, 2 pi electron here, and 2 lone pair of electron here, which are in conjugation with these 4 pi electron. So it consists of 6 pi electrons. So it is a aromatic hydrocarbon, and it is also a planar molecule because each carbon atom in this molecule is sp2 hybridized. So all the orbitals are in the same plane. So this is a planar molecule. The bond angle at the sulfur is around 93. This carbon, sulfur, and carbon, this bond angle is 93. And the carbon-carbon sulfur bond angle is 109. So this bond angle is 109, and this bond angle is 109, while this bond angle is 93. And the carbon, this carbon bond angle is equal to 114, and this one is also 114. The carbon-carbon double bond is generally approximately equal to 1.44 angstrom, but in this case, in the presence of sulfur, this carbon-carbon double bond length is equal to 1.34 angstrom, and the carbon-sulfur bond length is generally larger, and it's equal to 1.70 angstrom due to the larger radius of the sulfur atom. And the carbon-carbon bond, single bond length is equal to 1.41 angstrom. Physical property, thiophene is a colorless liquid with benzene-like odor. Generally, the sulfur-containing compound have unpleasant odor, but thiophene have little pleasant odor, and its odor is like benzene. In most of its reaction, it resembles benzene. As benzene is aromatic, consists of 6 pi electrons. So this thiophene molecule is also aromatic. It consists of 6 pi electron and planar molecule. So its most electrophilic substitution reaction is resembled to the benzene. As it is a colorless liquid, it boils at around 84 degrees centigrade, and intensity is 1 gram per ml, which is approximately equal to the density of water. Now, natural occurrence, thiophene and especially its derivatives occur in petroleum. And natural thiophenes are characteristic secondary metabolites of plants belonging to the family Asteraceae. And here are some naturally occurring thiophene molecules. This is thiophene, biothiophene, and this is terthiophene. It consists of 3 thiophene units, and it consists of 5 thiophene units, so it's known as quinoquine thiophene. And these molecules are generally present in the plants belonging to the family Asteraceae, and here are some images of Asteraceae family. So naturally, the thiophene molecules can be isolated by the petroleum, or either it is present as a secondary metabolites of plants belonging to the family Asteraceae. Now I will discuss about the synthetic method, that how we can synthesize thiophene in the laboratory. So various methods are available for the synthesis of thiophene in the laboratory. I will discuss some of them. The first one is the Paul-Knorr synthesis, which is a well-known reaction for the synthesis of thiophene. The second one is Hinsberg thiophene synthesis. We can also synthesize thiophene from the reaction of 1,4-dihalo or diene. We can also synthesize thiophene from the conjugated alkynes. And industrially, there are several methods available for the thiophene synthesis. So I will discuss these synthetic methods one by one. So starting from Pal-Nor thiophene synthesis, the Pal-Nor thiophene synthesis allows the generation of thiophenes by condensation of a 1,4-dicarbonyl compound in the presence of an excess of a source of sulfur such as phosphorus pentasulfide or Levinson reagent. This is the 1,4-dicarbonyl compound, position 1, 2, 3, and 4. So 1,4-dicarbonyl compound is when treated with a source of sulfur, and that source of sulfur may be phosphorus pentasulfide or Levinson reagent. This is Levinson reagent, which consists of hydrogen sulfide, hydrogen chloride, and water, or consists of phosphorus P4S10, which is also a source of phosphorus. So many mechanisms are reported for the Pal-Nor synthesis, thiophene synthesis. And one suggested mechanism is that the sulfur source produce atomic sulfur, and this sulfur replace one of the carbonyl oxygen and producing in the first step this intermediate species. And the counter line take one of the hydrogen from here, so a unsaturation is produced over here, and hydrogen is taken by this sulfur atom, so producing this intermediate species. So both of these compounds are in equilibrium with each other. And then the second step, when the lone pair of electron of the sulfur attack on the second carbonyl compound, it produces another intermediate species. And when a water molecule is eliminated, hydrogen from here and hydroxyl from here, one can obtain the substituted thiophene molecule. This is one of the suggested mechanism. The second suggested mechanism for the Pal-Nor thiophene synthesis is that the thiophene synthesis can occur by bis ketone intermediate. So it's also possible that the 1,4-dicarbonyl compound, when reacted with the sulfur moiety, both the carbonyl oxygen is replaced by a sulfur atom, and then hydrogen sulfide is eliminated to produce the thiophene molecule. This mechanism is reported in Science of Synthesis in 2000, and the paper which was published in 2000. So both the mechanism are acceptable and published in journal in different papers in different journals. So both the mechanism that either the bis thioketone is formed, or only one of the carbonyl oxygen is replaced by a sulfur atom to produce the thiophene molecule. Pal-Nor thiophene synthesis, there is another example reported for the thiophene synthesis, that thiophene can be synthesized from 1,3-dicarbonyl compound when it is reacted with thioglycolate, and it produces thiophene 2-carboxylic acid ester. So this is 1,3-carbonyl dicarbonyl compound. In the previous slide, I have mentioned the 1,4-dicarbonyl compound. When 1,4-dicarbonyl compound is reacted with sulfur moiety, it produces a thiophene molecule. But it also reported that the 1,3-dicarbonyl compound also produces a thiophene molecule when it is reacted with thiophene 2-carboxylic acid ester. And the 2-water molecule is eliminated to produce the thiophene molecule. The mechanism is mentioned over here, that in the first step, this reaction proceeds in the presence of an acid. So it's protonated in the first step. And then the sulfur, which carrying the lone pair of electron, attack on this carbon atom and producing this intermediate species. And then water molecule is eliminated, hydrogen from here and hydroxyl from here, so producing an unsaturated species. And also this protonate this oxygen atom. Then this hydrogen is eliminated, And when the lone pair of electron shift toward here, this pi electron attack on the other carbonyl carbon atom, which is at third position, and producing the thiophene molecule. This synthesis is also reported in Science of Synthesis, which was published in 2000. The second method is Hinsberg-thiophene synthesis. And the synthesis of thiophene carboxylic acid from 1,2-diketones and dialkyl thioacetate via intermediate of sigma lactone in the presence of sodium or potassium alkoxide is referred to as the Hinsberg reaction. This is the Hinsberg reaction. It is a 1,2-diketone, and this 1,2-diketone is treated with a dialkyl diacetate molecule, and by the reaction of these two species, in many steps we can obtain the substituted thiophene molecule. It's involved many steps, and the mechanism I will show you in the next slide, that it involves many steps in which the 1,2-diketone, when it is reacted with the alkyl thiodiacetate, it produces the thiophene molecule. So the mechanism is mentioned over here, that this ester molecule consists of an alpha proton, which is highly acidic. So in the presence of base, one can eliminate either this proton or either this proton. In this case, when this proton is eliminated, a negative carbanion is produced over here. Then this carbanion attack on the 1,2-diketone to produce this intermediate species, and then this negative oxygen atom attack on the second carbonyl ester and producing this intermediate species. And when this lone pair of electron come back, the ethoxide ion eliminated, and this ethoxide ion take a hydrogen from here as mentioned in this step, and then this bond break and producing another intermediate species. And then in the presence of base, the second alpha proton is eliminated, a carbanion is produced, and that carbanion attack on this ketone, and another intermediate species is produced. And in this case, it is treated with ethanol molecule, and it's get protonated. And after that, the ethoxide ion take this hydrogen atom. So an unsaturation is produced. A water molecule is eliminated in this step and producing the thiophene oxalate ion, which is protonated with the solvent and producing the substituted thiophene molecule. The third method is that we can obtain the thiophene molecule from 1,4-dihalodiene and copper catalyzed tandem sulfur alkylation of potassium sulfide with 1,4-diiodo 1,3-dienes enable an efficient synthetic approach to variously substituted thiophene. As one can see over here, this is the 1,4-diiodo 1,3-diene molecule, and when it is treated with potassium sulfide, a 3 equivalent, and in the presence of copper iodide 0.1 equivalent, and acetonitrile solvent, when it is heated at 140 degrees centigrade, one can obtain the thiophene molecule. And this reaction is reported in Organic Letter, one of the most important journal of organic chemistry, and this reaction was reported in 2010 by these scientists. The fourth method is that we can obtain thiophene molecule from conjugated alkynes, and the 1,3 conjugated alkynes react with hydrogen sulfide under basic condition to produce the thiophene. This is the conjugated dialkynes, and when it is treated with hydrogen sulfide in the first step, the lone pair of electron of sulfur attack on this carbon atom. So the pi electron take one of the hydrogen from water solution, because sodium hydroxide take one of the hydrogen from hydrogen sulfide to produce a negative ion on the sulfur atom. This sulfur attack on this carbon atom, and then this pi electron take hydrogen from the water molecule and producing this intermediate species. And in the second step, the lone pair of electron of sulfur attack on the conjugated diene molecule, this carbon atom, And this pi electron take another hydrogen atom from here or from water solution and producing the thiophene molecule. The last one, there are some industrial methods available for the synthesis of thiophene. And the first one is that when the N-butane is heated at around 560 degrees centigrade with sulfur, it produces the thiophene molecule as well as the hydrogen sulfide gas is eliminated. The second industrial method is that when the alkyne is treated with hydrogen sulfide, in the presence of alumina catalyst at around 400 degrees centigrade, then one can obtain the thiophene molecule with the elimination of hydrogen gas. And the third industrial method is that we can obtain thiophene molecule by treating sodium succinate with phosphorus trisulfide to obtain the thiophene molecule. So these are some industrial methods for the synthesis of thiophene molecule. So in today's lecture, I have discussed about the structure of 3-membered, 4-membered, 5 as well as 6-membered sulfur containing unsaturated heterocycle. And I have discussed in detail the natural occurrence of thiophene molecule and physical and chemical properties of thiophene molecule as well as various methods for the synthesis of thiophene molecule, some laboratory method as well as some industrial method for the synthesis of thiophene molecule. Here are some reference books for further study. Thank you.